Today we're going to look at directed graphs, which is another graph processing model that's very useful in many applications. It's very similar to the undirected graph model that we looked at last time, but there are some really profound differences. After introducing the concept and looking at the API, we'll look at three important classic algorithms for processing directed graphs. The introduction has to do with just explaining the concept and seeing what it does to our graph processing problems, like the ones that we talked about for undirected graphs last time. So the idea is that the edges now have direction. A directed graph, or a DiGraph, is a set of vertices that are connected pairwise by directed edges. So it's a list of pairs of vertices where the order of the pair matters. So an edge, we say an edge goes from one vertex to another one, whereas undirected graphs, we just talked about connections. When we're processing such graphs or traveling around them, we have to follow edges in the given direction. So for example, if we talk about a path in a DiGraph, it looks like there's a connection between 2 and 0, but only goes from 2 to 0. If you want to go from 0 to 2, you have to follow the edges in direction, going from 0 to 5 to 4 and then to 2. In a directed graph, in this DiGraph, you can't see 2 directly from 0. Similarly, a directed cycle follows the edges around the direction to get back to the original vertex. Also, vertices have in degree and out degree in DiGraphs. And the out degree obviously is the number of arrows leaving the vertex, and the in degree is the number of arrows coming into the vertex. Those are the basic definitions. Let's look at a couple of applications. One obvious one is road networks, where we put a vertex according to intersection and an edge for roads, and we look at a situation where the roads are one way or can be one way. So if you've driven in lower Manhattan, you're very familiar with this map, which has lots of one-way streets, and it's not always clear how to get from one place to another. You can have some two-way streets that have edges in both directions, but with DiGraphs, we allow the abstraction of one-way streets. Here's another more abstract example. This is the political blogosphere with connections if blogs have links to one another. As you can see, most of the links go from blue to blue or from red to red, although there are some orange links that go from blue to red and a few purple ones that go from red to blue. And this gives some insight to the communications in the political blogosphere, at least in 2004. Here's another one. This is a study of the crash in 2008, and it was a directed graph that showed the structure of banks lending to one another. An edge corresponds to an overnight loan, and a vertex corresponds to the bank. From studying this diagram, experts could see how the banks divided into groups and were therefore vulnerable in these groups. And we'll look at more detailed definitions of how these groups are defined a little later on. This is just an example of the use of a DiGraph. And it's a DiGraph. One bank lends money to another. That's not the same as the banks being connected in as in an undirected graph. The direction really matters. This is another one from logic, where the vertices correspond to Boolean variables and the edges correspond to implication. And people use graphs like this to study in logical verification and also studying electric circuits. Electric circuits themselves can be DiGraphs, where circuit elements have input and output. And so the edge takes the output of one element to the input of another. Trying to understand the behavior of such a circuit involves processing a DiGraph. Here's another abstraction, the so-called WordNet graph, where vertices correspond to what's called synsets and edges correspond to hypernym relationships, where a word is an instance of another one. So there's a lot of different events, like a miracle or human activity, and so forth. And graphs of this type are very useful in studying applications involving meanings in human languages. Here's a famous one. General McChrystal said that once we understand this graph, the war in Afghanistan will be over. So with all these types of applications, and there's many, many others, just as with graph processing, the DiGraph as a model distinct from graph processing is important. There's many direct applications where we have connections between objects, but the direction of the connection matters. So what about DiGraph processing algorithms? Well, we're going to look at many problems that are very similar to the ones that we looked at for undirected graphs, but you can see that they're going to be a bit more complicated. Even a human has trouble looking at a digraph, trying to figure out a simple problem like, is there a path from S to T in this digraph? Seems like there's quite a few possibilities to consider to convince yourself whether or not there's a path. And for the huge digraphs examples that I looked at before, obviously we're going to need a computer program, and we're going to have a bit of a challenge figuring out what's going on. Of course, you might want to know the shortest directed path from S to T. For example, if you're driving around Lower Manhattan, you certainly want to have a solution to that problem. Then there's another problem called the topological sort problem, which is a general model that's useful in all kinds of applications where we're scheduling events that involve precedence constraints. In the graph abstraction, or the digraph abstraction, it amounts to the problem of trying to draw the digraph so that all the edges point up. That's called topological sorting. And then connectivity is more complicated for digraphs than for undirected graphs. There's the concept of strong connectivity, which means for any given pair of vertices U and V, you want to know, is there going to be a directed path from U to V and another directed path from V to U? That's a much more complicated problem than connectivity in undirected graphs. A generalization of that, or a query related to strong connectivity, is so-called transitive closure. And for that, you just want to be able to answer the query, given vertices V and W, is there a path from W to V? That's transitive closure. Actually, you're familiar with the web as a gigantic directed graph. If there's a link from page A to page B, that's a directed edge. And digraph processing is used in famous PageRank algorithm to determine the importance of a web page. Those are just a couple of examples of digraph processing problems that introduce the idea.